Very pleased this evening to welcome you all here to AREG's meeting for April, and hope you didn't miss us in March while the hall was busy being used for the state election. Very happy tonight to introduce to you Jeremy, VK5 CIA, who has been at me for quite some time to come and tell us all about the magic of software-defined radio. Yes, you have. So without any further ado, I'll introduce Jeremy and give him a round of applause, please.
Good evening. So we're going to be looking at software-defined radios. This comes from a lecture series which is about 20 hours long. I'll try to keep it to somewhere south of 19 if you like. So it's just an overview of all the major issues. Behind it, there's quite a bit of research which I can give anybody who wants access to that's online, and we'll go into a lot of the areas a lot deeper. But I'm going to try to keep away from too much of the maths, just look at what are the capabilities of the software-defined radios, how they're being used, what the model is, and he wants me to talk in louder. Got it? Yeah, I'll face the screen. Come out. What I want to first of all do is just touch on a bit of history, because a lot of the software-defined radio picks up the mathematics and theories of the past, and it's quite interesting how you go back 400 years and we start to look at a number of the things that were brought up. So it's probably scary to a number of the engineers here as we look at the different types of theories that came out. But back in the 800s is when we started to talk about Fourier theories, the starts of it. Then in 1928 is the first time we started to talk about the Nyquist sampling theories. Nyquist sampling theory says that if you've got a 1 meg of signal, basically you should be monitoring, taking samples of it about 2 times the speed, plus a bit. Then Shannon's theory came out at 1948. We had a lot of things happen during the war. There's first start of radio, a lot of communications. When you see this online, it's probably got about 40 different things in there. I've just hit on the major events. So we started to understand what's the maximum amount of information we can put in a bandwidth and a frequency, which is a very short version of Shannon's theory. Then in 1970, we started looking at the first of the DSP chips. So this is the defense chips that are really happening about this time. This is not the ones that are generally available to you and me to buy, because they were very, very expensive. So about 1984, we start to see a development of the software-defined radio environment for military, and it starts to expand out. Then the military program's about 91. Speakeasy, you've probably heard about Speakeasy being a telephone. That is not the telephone system, which is their secure system. This was actually the use of SDRs within projects for defence. And then 1996 is actually when the software-defined radio forum started. So it's very new. I finished my degree in 1986. So this is before a lot of these types of use of the theories into signal processing. So now let's just see, what does it mean, software-defined radio? So the first of the software world started about 1984. We started talking about a software-controlled environment. In 1991, we started to say software programmable radio. And then in 1992, that's actually the first start of it becoming publicly an area of software radio. All the way down again to really the 90s. And what happened in the 90s is the first time we started to see analog to digital chips that were generally available. Qualcomm came out with them about 96 as a commercial product. So before we could do analog to digital cheaply, we have a major problem not being able to do a software-defined radio. So the development of your analog to digital front end was very important for the development of software-defined radio. Yep. I'm selecting them each time. So let's just talk about the front end of it. Very important to understand the front end and how it's being used, because this is where we have a lot of problems with software-defined radios, especially the broadband ones, which we look at them. They get overloaded with AM radio, FM radio, digital system, TV, all which are extremely strong signals. So if you're trying to receive in any of those type of areas, you're always going to have a problem to make sure you can keep that signal down below the maximum input to the receiver. Otherwise, it distorts. The three major points we have here for the types of radio, the super heterodyne, everybody remember from their license, was really the starting point, which is we down-converted to a frequency and then did an A to D on that frequency. Then you've got the direct conversion. That's only really been generally available for about the last 15 years, which is it's receiving the full bandwidth from the outside world and doing a direct conversion to digital. That happens today up to about 2 gigs. For your more expensive ones, the ones that you and I would buy, probably in the area of 500 to 600 megs, is about the top end before it starts getting very ridiculous in price. Next one. Remember that. Just select the next screen. Got it? Right, analog to digital conversion. There's 2 major types which come out, and it's really important to be able to understand the difference between them. The flash ADC is basically the one that you'll probably know the most about. It's basically using a ladder approach between capacitor and originally resistors, and it used a lot of power, and it gave the output generally about 8 bits. The pipeline was a development of that which speeded it up, used less power, but it took a little bit longer in time to be able to do it. Sigma Delta became very popular because of the CD game. The CDs are converted, generally the audio in CD is a 1-bit input data, but it's no longer just doing 1-bit conversion. It looks at 1 bit for, is it bigger at a higher voltage or a lower voltage than the previous time we sampled? And then for Sigma Delta, we tend to use frequencies of somewhere in the area of 50 to 100 times the normal sampling frequency. And that's because it allows us to convert into higher bit resolution mathematically down the line. Then the improvement of the inline flash process is the SAR. And the SAR, and I've just lost the terminology, is a feedback mechanism which you'll see in some of the radios that they look at their output signal and compare it to the input signal and then adjust the input signal such that it's corrected for any non-linearity. This is what's done purely inside of the ADC. So it comes in analog, it's converted to digital, it's converted back from digital to analog as a part of the feedback, and then it's compared to the original signal. And that's done on each bit. Next. Oh, okay. Nyquist-Shannon theory. This is very important to understand the theory, but it's also got some limitations. So Nyquist said we want to monitor at about 2 times your frequency. That's correct for real sampling. We have 2 types of sampling. We have real sampling and we have IQ. So when we're going to start getting into words like complex mathematics, which is the mathematics of unreal numbers. Unreal numbers are used for the definitions of 2 dimensions at 90 degrees to each other. Be very careful. The use of the mathematics term unreal is irrelevant. It is totally real. It's just a mathematics term. So what we have in the Nyquist domain is talking about only real to real signals. And the reason that Nyquist didn't actually have anything to say about IQ is it wasn't invented and it wasn't talked about in 1928. It was about the late 30s as a part of radar work that they started to understand there's another way to mathematically manipulate a signal. And that's the big thing to remember. Anytime you go down IQ, it is breaking the signal into two components which are mathematically easier to work with. It may look complicated, but it is significantly easier to work in IQ with most modulations and techniques than it is in real. Next. So IQ is made up of two components. There's a phase component and there's a quadrature component. The important part to know, though, with IQ is there's a significant advantage to it when we're coming to the A to D sampling side. When we have the output as real, it must be sampled at twice the frequency. When we sample in IQ, you only have to sample at the frequency, plus a bit. But it's literally minor bit. It's the same issue with Nyquist. It's always twice plus a little bit. It's the same with IQ. The part that you're also going to remember is there's two components. So the total amount of data that we get out of IQ is the same as real. But it is mathematically easier to calculate with and to work out, especially our complicated communications, like what we use in 5G, 4G infrastructure. But even for FM, most of your information is sitting in your quadrature. So being able to very easily take that information out is the advantage of IQ. I think we're halfway through the whole lecture series so far. Right, fast Fourier transform. Once we've got a digital signal, it's very important that we be able to do different types of calculations with it. The fast Fourier transform is changing from time domain to frequency domain. Your standard old oscilloscope, compared to your frequency analyzer. You can move between those two domains easily. Being able to move between those is very useful for different types of filtering and decoding. So the other part associated with fast Fourier transform was the discrete Fourier transform, which is a simplification for the mathematics, for us enables us to do this type of work very easily and quickly in especially a field programmable gate array, FPGA. Windows, yep. Field programmable gate array. They're not in all your SDRs, but generally everything comes out with them these days. Why? Because a field programmable gate array can decode, do mathematical calculations, do multiply, add, divides very simply. So this is where we can start to look at all our different types of conversions. We want to be able to move, especially if you're looking at the higher frequencies up around 1 gig. If you want to be able to take a 1 gig signal that, say, has got 100 megs of data on it at the top, so from 900 through to a gig, if we're running in the IQ domain, we can multiply that by the frequency we're going to download it to, which is 100 megs below, and then filter it so it's only the first 100 megs of data. And then we can cut the data short because it's now got excess information on it, which is our down convert. The ability to use the field programmable gate array to be able to do these types of things is significantly faster and quicker than using your Intel chip on your computer. And it's sitting right next to our analog to digital converter. So as we look at the different types of ones down the bottom here, the Pluto SDR. Pluto is a very popular development. There's a lot of it in education. So that's using a combination of processors, but there's Zinc 7010, which you'll see quite a bit around. It's one of the cheaper whole versions of the field programmable gate array. We will look at the other type this down in a minute. There we go, that one. So the next part is we find CPUs and memory in the SDR. So being able to take information out of your FPGA and present it in different ways has become very important. So some of the FPGAs now have the single core and multi-core ARM chips as a part of it. The RX888 is a great example of that. It's got it built into the field programmable gate array, which means that data can move very quickly between your CPU and the mathematical calculations. Then the CPU then starts to give us our web interface, a REST API, and all the different types of ongoing analysis work that you don't normally have happening just inside your FPGA. The reason we do it in the PC is it's simpler to have the flexibility there sometimes. But if you wanted something as a permanent operational single task environment, you would always put it into the field programmable gate array. Clocks. As we look at the signal conversion from analog to digital, timing is so important. If we have movement in time, then we start to get quantized noise that comes into our signal. The big advantage with digital is once it's converted, it doesn't have noise added to it. In the analogs world, every time we do something with a signal, it adds noise. In the digital world, as long as it's the same quantized size and we're not changing the data itself in any major way, it doesn't add noise. It allows us to do all that process without adding noise to it. What's very important with the clock side is when we're starting to look at time of arrival, which is when you're doing your DF, direction finding, you want to find if you've got multiple signals. This is becoming very important for AIS, which is your ship's location, ADSB, which is your aircraft. We're seeing quite a bit these days of the military disguising that because they don't want to be seen in different parts of the straits, or their aircraft is going past Ukraine especially, and they don't want it to be known exactly where it is. So when you've got a good clock, and we're talking about accuracy sub 10 to the minus 6, 10 to the minus 7, that's when you can start to say you can do reasonably accurate distance calculations to your transmitter. Most of this work tends to happen in digital signals. Digital signals are a lot easier to do calculations on than analog signals. Why? Because they've got a known form, and we can calculate against that known form using a mathematical process which is called convolution, which in a very simple term means I know it looks like that. So when I've got a filter above it that perfectly lines up with it, I've got the signal. And this is imperative that our clocks are working very well. Parts of this work we see with the RTL4 as a part of the key, what's the one that Mark's got? And is Kraken, thank you. The reason that works so well is it's got one clock system, and that clock is working between all of the devices, which then allows for direction finding. But that's doing it primarily in the analog domain. Interfaces. This is scary. Anytime you look at USB, it doesn't matter how fast they say it goes, it's how well does that USB time onboard your processor, especially if you're looking at some of these ARM processors that only got 2 cores. The timing is just abysmal. And what will happen is you'll tend to lose some of the packets because it's using a large percentage of the available bandwidth, and a timing or a buffer goes out. So especially if you're working with ARM processors with 2 cores, one of the ways that minimizes this is to allocate the core primarily to running that driver function. But then it's got other things to do. So then we get up to the gigabit Ethernet, And you say, oh, well, at least we're getting a lot better speed. But again, how good are the drivers? The problem we have with a lot of the software that we use in the commercial world is the drivers are as old as anything. And we're trying to run new equipment with old drivers. So the timing becomes a significant issue with these two here, the 10 gig and the 1 gig. Understanding the timing that is associated with the data that's coming in, the main way we beat that is that when we do the conversion, we tend to put a tag on it with the time. We can't rely that it's going to stream at the same rate all the time. It doesn't. PCIe 4 does have a timing control to it and can have a priority over other types of traffic, but you've just spent quite a bit of money. It's probably 10 times as much. So the software system that we got out there for driving these is there's a number of different groups from the software. You've probably heard of the SDR++ and the hash, which are two of the major ones. The one that's becoming very big in the market, GNU-based systems, is really leading in a lot of development. The US military, as their what used to be called Department of Defense, now called the Department for War. I nearly got that wrong. They have said they want to be using GNU radio as the base for a lot of their definitions of 6G and communication systems that are going to be used in the military. So we then have got different frameworks for these that are getting, well, the whole GNU radio is doing a major change. Version 4 of that just got released at the start of this year. It's only been out since version 1, it's been out about 15 years. It's getting to a stage where it's nearly production capable. And the difference between these packages, the SDR general packages and the GNU radio, is GNU radio is like a C compiler. It's made for the RF environment, and you want to do different decodes and things, it's got the blocks for doing that. It's purely a radio system communications infrastructure that allows you to play with the different signals. All right, let's have a quick touch on some of them. This, by the way, the RTL, forget about version 4, just the RTL SDR, that is one of the big reasons that software-defined radio today is working. It was a device that was originally made for receiving television signals. It came out in approximately 2008, 2010, somewhere around there. I should have put the date up here. But because it was a $30 device that when hacked and reconfigured in another way can receive from 24 megs up to 1.7 gigs. In fact, it can also go down to about 1 meg. So this is an 8-bit software-defined radio that generally today we like more than 8 bits. It'll receive your FM, it'll receive all your communications today at as long as it's got a reasonable signal, and it's capable of being able to go all the way up to decoding GPS satellites. Now, GPS satellite is a whole lecture in itself, but it is a very complicated collision detection, multi-axis type approach, not collision, code division, multi-axis, sorry. That a software-defined radio can set up and make very easy to decode. And so the RTL4 can actually, whole series can do it. AirSpy. This is a very interesting one. This is one of the very few types of software-defined radios that actually has given its sensitivity, all its specifications. However, the HF Plus is a narrow band receiving device. And so we're going to be very careful between them because the different devices have got different bandwidths. And the bandwidth that the AirSpy works best at is less than 25 kHz. But you probably will not find a better HF receiver out there. Doesn't matter about the money. that device is amazingly good for HF signals. The Pluto SDR, this is the number one education one. It was bought out by Analog Systems about 10 years ago. It was used extensively in the schools. It was moving up to a 12-bit infrastructure, and it's also got a 61 mega samples per second. And it was able to do IQ. So you can actually receive the whole of 61 or 60 megahertz of receive. That's the same receiver that the Web 888 uses, by the way. So this is a broadband receiver, and you've got to be very careful when you put these two alongside each other. They're totally different type of devices. Not only is this one 18 bits and this one's 12 bits, its bandwidth that it's focused on is completely different. The RX888 Mark II, this is, we're using on this, I believe, out at our receiving station, that's right? Yeah, yes. So this is just a USB connected receiver. It is ridiculously sensitive. It's able to receive 60 megahertz from 0 to 60, and it'll do it all day. And its partner is called the Web 888, which has got a ARM processor and a web front end, and it does decoding as well. HackR F1. This is a very interesting device. If we just talk about what it was originally designed for, which was being able to do half duplex, in other words, it can transmit from 1 megahertz up to 6 gigahertz. And it does all of that frequency very well. I've got one here. If you do have one, be very careful with it because it can transmit on a number of frequencies that you should not be transmitting on. Even though it's low power, a good example of that is the GPS frequency. You look at the regulations, the maximum you're allowed to transmit there is minus 73 dBm. It puts out quite a bit more than that. And you do not want to be involved in transmitting on those frequencies and getting caught. It is not good. Then our USRP, this group, Etis Research, brought these out. They were one of the first to get involved with the GNU radio. This is the start of a professional series in that it's used some of the chips that are the same, which are the analog front end, but they've put more complicated field programmable gate arrays. And they've also made it, when you start up the device, some of them, you actually load up your field gate array image every time, which gives you huge flexibility. So just going through what we've looked at, and then I'll show some examples of the different equipment. The history, if those people are interested in actually getting into the deeper part of this, I've got a URL where you can see every part that I've talked about, and it's then got somewhere in the area of about 2 or 3 pages on every item. So it is very interesting to see the development of software-defined radio, where it came from, and how it's happened today. And that's mathematics from as far back as the 1700s, all applied into a digital environment. And it's really interesting to realise the first D to A's, it's about 1996 that was generally available. So a number of us who've done our degree before that, we knew the theories, but we weren't applying it into a real environment. Analog to digital converters, number of times, the Sigma Delta is what one that really sticks out as a very interesting approach. The Sigma Delta in that it's doing 1 bit, but it's looking level adjustment. The multi-bit input Sigma Delta, which instead of using 1 bit can use up to 3 and 4 bits, are able to get somewhere in the area of 18 to 24 bits of real data as their conversion. And it is all a part of a very complicated mathematical process, which would take a whole couple of lecture series just to talk about. Field programmable gate array, this is where a lot of the fun's starting to come up. being able to do more and more inside of it. It used to be very expensive to be able to get the compilers to do field programmable gate arrays. Today, there's a number of free versions that are available, and it means that you can develop an environment for decoding some special code. And from that point of view, your 4G types of environment, a number of these field programmable gate arrays can do it easily. And it's very interesting, their capabilities. Clocks, always going to be an issue with you. Accuracy is so important. You'll find a number of the SDRs come with an antenna capable of plugging in a GPS satellite. That will give one level of accuracy. The others have external clocking capability, generally at 10 megahertz. That, if you're going to run multiple devices, if you're going to do time of arrival, you must start looking at how you get best clock. Software, most of it's free. I would highly recommend, there's a lecture definitely coming up down the line looking about GNU Radio. It is an amazing tool. Its install on Windows is reasonably easy now, and you start to be able to map the mathematics of demodulation straight into a circuit diagram or a block diagram that is directly related. So especially like AM signal, you can actually see the 3 stages of making it on the GNU radio, and it will probably take you 5 minutes to do it. Nyquist and IQ. I would say most of the people that I tell people that IQ does not have the Nyquist limitations don't understand that IQ is totally different. So it's the same amount of data, but it's done at a slower rate. And as it's half the rate, and your cost on your D to A tends to be associated with the speed at which it's doing its conversions, the IQ has the advantage. In the analog sense, there are 2 versions here, and I'll just touch. There's an analog conversion that happens inside the A to D converter, which means that it has a signal passed through to it at 90 degrees, which allows it to calculate the Q component. When it's done in the digital, it actually comes out a real, and it's then mathematically converted. So it becomes an interesting issue associated with how they apply the conversions. CPU and memory. The memory used to be a problem when we're talking about 8K, but now you're talking about a gig that comes with some of these processors. It's usually defined by the field programmable gate array, the type it uses and how it's going to interface with it. But the CPUs and memory are very useful inside a number of the devices. Just remember, a software-defined radio can be everything from an A to D to the world. So we're talking about all the extra blocks that come into it. If you're running interfaces and you're going to get close to your bandwidth, just realize USB is going to remind you not to use any more than 50% of its bandwidth, if you're lucky. And hardware out there, if you haven't got yourself an RTL, I would highly recommend it, especially for GNU Radio, because that's one of the areas that they've supported very well. If you haven't started on GNU Radio, I would start on GNU Radio 4. I wouldn't start on 3. GNU 4 is nearly released as 1.0 in the next month. Show and tell. So that's the Web 888. That is the 60 megs of decode, web front end. Oh, there we go. Sorry. There's 2 games. There we go. You hold it. Here's the hand model. So this is the one, this not only decodes 16 different sessions at the same time of FT8, FT4, Whisper. It can also give you any of the frequencies between 0 and 60 for other types of input and flow.
How much more than
maybe $100 more. Yeah, it's silly. The capability of these is just ridiculous. Compared to the RX888, that's its brother. But that one also does slightly higher frequencies, but it's more focused on just being the receiver section, and it's about half the price, or 75% of the price. You want us to hand them out? Then we have the Hack RF. So this is a Hack RF with what's called a porta pack. Oh, yeah. There we go. The Hack RF has the porta pack is basically a CPU that goes on the front. So it's moving it from being equivalent to an R888 to a Web 888. But, excuse me, it's got a number of software developments that have been put in it. So it will allow you to do a lot of things that are not legal. So be very careful with it. Sorry? Oh, okay. This is the Pluto Plus, which is part of the Pluto series. The issue that what they've been able to do with the Pluto is increase some of the processing power, which is the 7010 was the FPGA that was originally. This one uses the 20, which is about 4 times more powerful. And then the A to D this uses, you'll hear about the 9361 is the main A to D, and a 963. The 63 is the junior brother. The 1 is the senior. The 63 is converted into a 61 by a software hack. It doesn't do the same type of bandwidth. It doesn't do the same type of minimum frequency, but it does things very well and costs a fraction of the slightly less price. So it is one of the most popular chips out there that's in the software-defined radios today. Then we got the TRX Duo. This is one of the very first send-receive at reasonable power. That does about 20 milliwatts of power. That unit was actually used by Ben Garton ABG to transmit a whisper signal at, we were getting at about 5 milliwatts, and we got 1,500 kilometres. So we got from Sydney to the north of New Zealand. And so it's a transmitter, it's receiver, it's duplex. It can do it at the same time. It's got 2 inputs and 2 outputs, 2 receive and 2 send. And it can be configured with multiple different types of software. But inside the GNU radio, it just becomes an amazing type of environment to develop. Then we come down to our specialist ones, but there's still, there we go, sorry, do another one out here. So this is a whisper transmitter that does all your whisper frequencies. It's effectively a ESP32 that's being run and exciting its digital ports up to 30 megahertz, sorry. And then it's got a mild filtering, but it's only putting out 20 milliwatts. But it goes through all your whisper frequencies and rotates with them every 2 minutes. And it's an interesting environment of being able to show what a SDR specifically made to do one thing can be, and how much. I think it's the new versions of that are like $40. NVA. It's a software radio. It's just the way It's got to transmit, it's got to receive, it looks at the reflections. It's not overly fast. It's only really quite cheap piece of equipment, but it does a job very well. So again, specialist version of software-defined radio, the NVA. SDR Play, one of the boys that are one of the top end of the amateur type software environments. They're very sensitive. They've got reasonably good USB control. They tend to put out their own drivers for it, which means that it runs a bit better. And then we've got the RSP Duo, which is the same. It's the Big Brother version, which has got send, transmit, receive, and 2 channels. No, sorry, it's just receive, this one. But it's got 2 channels, and it's got its own balun on board, so you can give it a balance line in. Software radio. Generally it's the 818 or the 816 version of the chip. This is doesn't do DMR. The DMR is a slightly different version. It's $15 off-the-shelf chip, and that's doing 90% of the work of what this does. So each of these radios, the reason they're so cheap is because they're a single chip that's doing most of the work. One of the very first RTLs. And you can tell it's got that terrible antenna plug that was for putting in a TV antenna. It's extremely capable, amazing development, and that's what moved software-defined radio to the world. There's a more professional version of it, which is called the Fun Pro. Does it a little bit better, about 4 times the price. Slightly a bit better analog to digital conversion in it. And it's nice, it's got an SMA connector on it. So most of your RTL 4s these days, of which that's the version 4, SMA, thank God. $40, $45. That's your starting point. Anybody wants to go and play with software-defined radio, that's a great place. Why? Because there's lots of software out there for it. It works with Windows or WinSloth, and it will do all of the first tests that you want to do very easily. HF Plus. Those when we've had the exercise at Wollonga Hill, they were being used for the receiving section to show the waterfalls. That's poor thing, bored to tears on that. Its receiving capabilities is just absolutely ridiculous. It is, for the size, an expensive unit. You're probably looking at $200. But it is really fabulous as a receiver. Yeah, I think so. Right, that's the end of the show and tell. I dread to open the floor up to any questions. I've tried not to become too mathematical, but it is an area where if you want to understand how to program and how to use these devices, you need to be understanding some of the maths. The course that I work with at Flinders University, our first thing for all the engineers and the technicians that come in is to get them up to scratch with the maths again. Complex maths makes for easier decoding. It is not a complicated maths. It's just a mathematical term that you mustn't let confuse you. That our complex maths use imaginary numbers. They are a mathematical term that was brought up in, I think it was 1770s that originally started for that. And they didn't know what to use it for. They knew how it worked for trigonometry and for mathematical exercises. It wasn't until the First World War that we started to realise that that was quite useful for the radar side. And then it was only really exercised quite a bit later. Thank you very much. Hope that's been useful.